Hello everyone, welcome to MLC Math. Today we'll be investigating the connection between the Leibniz rule for derivatives, which we gave examples for in a previous video, and the binomial theorem, which is an essential ingredient in using the Leibniz rule. Let's go ahead and refresh our memory about what both of these are. The Leibniz rule tells you if you have two functions f of g and you want the nth derivative, you can do this as long as you have the binomial coefficients and you have the nth derivatives of the functions themselves. Well, the binomial theorem is a much simpler theorem in most senses. It tells you that if you wanted to compute the sum of two things to the nth power, you could do this as long as you had the binomial coefficients and you knew the nth power of the original things. And of course, the binomial coefficients are found by computing Pascal's triangle, which, if you want to get the coefficient of, say, x plus y squared, we know is x squared plus 2xy plus y squared. Well, you can obtain these coefficients from Pascal's triangle obtained by adding subsequent entries to get to the next one. Okay, so what we're going to show in this video, we're going to show the if and only if. So first we're going to prove the Leibniz rule by induction and use a special case of this for two functions, f and g, which we're going to explore further to derive the binomial theorem itself. And we're also going to go the other way around. We're going to not prove the binomial theorem, but we're going to accept that it's true since there are so many well-known proofs of it, and then use it to prove the Leibniz rule. So let's get started. Induction first. Okay, so this proof is going to start off like all induction proofs start off. We're going to state the theorem that we want to prove. We're going to prove it for a particular base case, assume it holds true for a particular integer n, and then show that it also holds true for the n plus 1 integer. Okay. Leibniz rule, just repeating. Nth derivative of n of f and g is the sum of n choose k, the n minus kth derivative of f times g to the k. So like I mentioned in a previous video, you can also write this as f to the k, g to the n minus k, and this actually helped us construct the table of derivatives in a previous video. And you can do this because it doesn't matter which one you call f and which one you call g, basically. Okay. Base case. Base case, we're going to use n equals 1, which tells us that the ordinary product rule, fg prime, is just equal to f prime g plus f g prime, which we know from elementary calculus. And it also satisfies this rule here, since it's just 1 choose 0 f prime g plus, I guess I'm writing them in the wrong order. It doesn't matter, like I said. 1 choose 0 f g prime plus 1 choose 1 f prime g, and these are both 1. So we wanted to show that this was equal to, and it was, since Pascal's triangle goes like this. This is 0 choose 1. This one is 0 choose 1. This one is 1 choose 0, and this one is 1 choose 1. So we see that they are equal from Pascal's triangle. And now the induction step. Assume that it's true for n. Now we're just going to look at n plus 1, see if we can use what we know about n to show that it's true for integer n plus 1 as well, which we can do. All right, so then fg to the n plus 1th derivative is just the derivative of fg to the nth derivative, which we know up here, sum binomial coefficients. Now the derivative just goes inside because it's just a sum. Derivative of f of n minus k g of k. Now we just use the ordinary Leibniz rule, which we already proved in the previous step, to simplify this expression. It is sum k going from 0 to n, and choose k. Now we're going to have f of n plus 1 minus k, g of k, differentiating the first term only, plus f of n minus k, leaving the first term alone, differentiating the second term. And now we're going to do a trick, basically. We want the summand to be the same for both terms. And if we do this, we want to peel off the 0th term, the n plus 1th, sorry, the nth term, and then see what we get from there. Okay. This is the tricky bit. Right. We're going to do this by letting k go to k minus 1 in the second term. When we do this, it becomes the following. K going from 0 to n. I then choose k. This one's the same. I need more room. I just need more room, guys. Okay. K equals 0 to n. And choose k. First term is the same. N plus 1 minus k g of k. Plus, when we do this, we have this one starting at 1, going to n plus 1. Let go to k minus 1. Okay, this becomes n plus 1 minus k. And this becomes g of k, exactly like what we want. We have k equals 1 to the n plus 1 of n plus 1 to k minus 1. Okay. Pretty sure. Let's check. No. This one does not change. This is the same. Okay, people. So now we have the same summand. All we have to do is simplify. Well, we have the 0th term here, k equals 0. So we're going to have, and choose 0, f of n plus 1 g. And then we're going to have the sum k equals 1 to n plus 1. I'm out of room again, guys. I'm out of room again. Got it right here. It's going to be small. I just don't have enough room. Okay. Plus k equals n plus 1 of n choose k plus n choose k minus 1. It's just bad. I'm sorry. Okay. N choose 0 f n plus 1 g plus the sum k equals 1 to n plus 1. Now we have n choose k plus n choose k minus 1. Thing that's the same for both terms. And we have one final term. We have the nth term, the nth plus 1 term actually. And choose n, f, g to the n plus 1. Okay, now we need an identity involving the binomial coefficients to show what this is here. Well, that's pretty straightforward. Remember how binomial Pascal's triangle was constructed? Let's give it another root row. 3, 3, 1. Okay. Let's look at this one here. So this is 0, 1, 2, 3. 3 choose 2. And 3 is the same thing as 3 choose 2. Well, we simply added this one, 1 which is 2 choose 0, and 2 which is 2 choose 1 together. So we have 3 choose 2 is equal to 2 choose 0 plus 2 choose 1, which tells us how we can generalize this. Basically, for our situation here, we're going to have this thing here is just n plus 1 choose k going to be equal to what we had before. N choose k plus n choose k minus 1. And this allows us to do what we want to do, basically. Okay, remember, this is n plus 1k. Yes. Now we can write this as final step, k equals 0 to n plus 1 of n plus 1, choose k, f. I'm out of room again. This proof is just too long. I need more boards. If anybody wants to give me some more boards as a gift, I'll be happy to accept them. Okay, final step. K equals 0 to n plus 1. N plus 1 choose k. F of n plus 1 minus k. G of k. So basically, I just took these three terms and put them back into a summation. So we are good to go. Making sure it's right. Yeah, should be good. Okay, there are most likely some minor errors, but this is basically how you do it. It is kind of tricky, but the main thing you want to remember about this proof is that you can use the binomial coefficient identity to prove it. Okay, so now we've got it proven. We actually want the connection to the Leibniz rule, which is the main thing I was interested in. The actual proof that you see here is pretty straightforward. It can be seen in most abstract and discrete mathematics textbooks. It's not really special by itself. But what is kind of cool is how you can use it once you have it proven to find the connection to the binomial coefficients. Okay. Okay. So we got it proven. It was kind of messy. It wasn't that fun, but this next part is fun. So now that we have this proven, we're going to let f of x be equal to e to the ax and g of x equal to e to the bx. We're just taking a special case of two functions. It's perfectly fine to do this. Okay, so this tells us that the left-hand side is equal to the nth derivative of the product. And of course, e to the ax, e to the bx is what we have up there. We can calculate this one pretty easily. It's just a plus b to the n times e to the a plus b x. Since anytime you have e to the something x, take the derivative of it, it's just going to be something to the nth power e to the something else. No problem at all. Okay, for the right hand side, it's also pretty easy. Okay, right hand side. This is equal to the sum, k equals 0 to n, and choose k. Now we have the n minus kth derivative of e to the ax, and we have the kth derivative of e to the bx. Well, we just use our exponential rule to simplify this. Sum k equals 0 to n, and choose k. Now we have a to the n minus k, e to the ax, b to the k, e to the bx, which we can simplify as sum k equals 0 to n. Gotta factor out some crap. Okay, we're factoring out an e to the a plus bx. Sum k equals 0 to n, and choose k, a to the n minus k, b to the k. And now all we have to do is cross out the e to the a plus bx on both sides. So now we have the binomial theorem. And we're good. We have finally shown that if we start from the Leibniz rule and we plug in these special functions here, exponentials, then we can get the binomial theorem. This was the main thing that got me interested in making this video. I'd never seen this correspondence before. It's something I'd always wondered, since we see these coefficients in the rule and we use the Pascal's triangle just the same. Just a second, I need some water. Okay, now we have that done. Let's work in the other direction. Let's assume that the binomial theorem is true and show that the Leibniz rule follows from it. Okay, people. Hardest part of the video is over. I apologize for the induction proof. It's necessary. It's a necessary component of the video. I don't particularly like the proof that much. It's okay, I guess. It's just kind of tedious with the renaming of the indices. When you look at it, it doesn't look that bad, but when you try to do it yourself, it's kind of bad. All right. Binomial theorem. We have taking a sum of two things to the nth power is simply the sum. If you have the coefficients of a to the n minus k, b to the k. We're going to assume this is true and get the Leibniz rule from it. Okay, let's proceed as follows. So we know that, how should we proceed? How do we start? Yep, we start with the first derivative. If we have two functions, take the derivative. It's just equal to f prime g plus f g prime, of course. And we're going to define new operators. A derivative only acting on f plus a derivative only acting on g, so that we can factor it out. So this is kind of weird. What is df fg? Well, df fg is simply g df by dx, of course. Same thing for dg. That's all we're doing here. We're just defining this new operator that only acts on one of the two functions so that we can write it as a sum. And you can probably see where we're going from here. Okay, now all we have to do is take the nth derivative. It's just the sum of the operators multiplied by itself n times in our original functions. And we're going to assume that the binomial theorem, which we know holds for numbers, also holds for differential operators, which does in some circumstances. In any case, this is not a very mathematician-approved proof. It's more of a physicist's proof. And let's see where it goes. Sum k equals 0 to n, and choose k. We have dfn minus k dgk acting on fg. Now, the whole point of the derivatives is that they only act on one function. So we can pull them out. Becomes sum from k equals 0 to n, and choose k, the f derivative acting on f, times the g derivative acting on g, which is just, of course, the regular derivatives of both functions. Which is, of course, the general Leibniz rule. And we are down here. Leibniz rule, yeah. Okay, that's it basically. If you like this, feel free to subscribe to my channel. I'll see you next time. Have a great day.